In this video, I will talk about big O notation. This is the main topic of this video, but we will start from the growth of a function. In mathematics and in computer science as well, we know the importance of a function, two functions, comparing two functions, which one is bigger, which one is smaller. So that's the topic of today's talk or today's video. So first of all, let me just put a scenario in front of you. The scenario one is scenario one. Suppose that you are given one candy on day one. Let me just make a table for that. Here we have day and here we have number of candies. You can assume that on day one we get one candy. On day two you get one another candy. It means that 1 plus 1 you have two candies. On day three you already have two candies and you get one more candy, and the total candies you have is 3. So you continue with that, and after 20 days you have number of candies with you are 20. So there are 20 candies after day 20. Now take a look on another example, another scenario. Another scenario is like that, scenario 2. Scenario 2. Suppose instead of getting one candy each day, you get double every new day from the previous day. So we make a table out of that. Suppose we have day, column day, and the number of candies with you, number of candies in scenario 2. On day 1, you have one candy that is given to you. On day 2, since you are getting double of the previous day, then you have two candies. And similarly, you have, when you have day 3, then you get double of that 2. So you get 4. Day 4, you get 8. 2 4s are 8. For 5, you get 16, and so on. So you can continue with that, and at the end, at day 20, how many candies you have over here. In scenario 1, we have number of candies are 20 at the end of day 20. But here, how many candies you have over here? We must have some formula for these number of candies, and that formula is 2 raised to power n minus 1. That is the formula. How this formula works: when n is equal to 1, you get 2 raised to power 0, and we have 1. When n is equal to 2, for example, 2 minus 1, we have 2 raised to power 1, and we have 2. Similarly, when we have n is equal to 3, then 2 raised to power 3 minus 1, which is 4. So you are getting all the candies by this formula. So we have the formula 2 raised to power n minus 1. So when we put 20 minus 1 on day 20, how many candies we can have? 2 raised to power 19, and this is equal to 5 to 4, 288 candies. These are many number of candies, around zero point 0.5 million, zero point 0.5 million candies. And how many candies did you have on day 20? You had only 20 candies. But here you have 5 to 4. You have 5 to 4.5 million, around 5.5 million candies. There is a huge difference between these two. So what's going on over here? So here you have very new thing over here. On the left hand side, as you can observe that if you have 2 candies in one day, if you double the candies, you get the double. If you give double to the candies, then you get 2 times. It is a linear growth, I should say. It is a linear growth. Okay. So this is due to the linear growth. If you double the things, then you get double answer. It is similar to the mathematics function y is equal to mx plus c. They are directly proportional. If you double the domain, you get double the answer. That's how the linear growth work. What happened on the right hand side? This is not a linear growth. As you can see that as the number of days are increasing, number of candies are increasing exponentially, almost double each day. So such thing is called exponential growth. Exponential growth. There is a huge difference between these two. So linear growth is due to the function f of n is equal to n, and the exponential growth of this function is due to this one. If n is equal to 1, you have n is equal to 0. For example, you have 1, or you can say 2n minus 1. If you want to say that n is equal to 1, you have 1 and 2, 2 minus 1, 2, so on. So 2n minus 1. So it means that these two functions are, I should say, f1 and f2. These two functions are not the same in terms of growth. The growth of second function, this function is exponential. The growth of this function is linear. So it means that we should have some definition to tell us that how the function behaves. That's where the definition of big O notation comes. So big O notation, very important concept in numerical analysis, in computer science, and even in mathematics, real analysis, or functional analysis, wherever you use the growth of two functions. So how we define the growth of functions? We define the growth of function by using big O notation, growth of a function. Suppose we have two functions. We say that f of x is big O, order of g of x. It means that there are two functions and we say that f of x is order of g of x. It means that the one function f of x is always either less than or it is equal to c some constant of g of x. Since in growth we are not interested in negative values, so we put the mod over here. F of x is less than or equal to c g of x. Or we can also see that f of x divided by g of x mod is less than or equal to c. We can also write this as follows. Anyway, this function is either equal to g of x or it is smaller than g of x. That's how we define the big O notation. But remember one thing, when you compare two functions, these two functions, the first function, this function is not smaller than g of x from the start. There should be some domain value where x is greater than k. So we write whenever x is greater than k. In that case, this definition holds. So in this definition, we require two things to find. One thing is to find the capital C or C constant. And another thing that we should know is x should be greater than some constant, some k. It means that when we have two functions, you draw this on xy plane, then this should hold when x, there is k, when x is greater than, x is greater than, x is greater than k. It should be here. I will talk about that in the next example. So big O notation says that if you say, for example, f of x is order of g of x, it means that this function is either equal to g of x or it is smaller than g of x. Okay, when you say, for example, f1 of x, let me just do some practice. f1 is order of g1x. It means that f1x mod is less than some constant c1 and g1x mod. If I say, for example, f2 of x is order of g2x, it means that this function is smaller, on the smaller side, or it is equal as well. So C2, G2X mod, so on. That's how we write the definition. Let me just solve some example for you so that you can understand it clearly. Example. So the example is show that f of x is equal to x square plus 2x plus 1 is big O, order of x square. I am writing this little bit big so that you know this is big O notation, since there is one other notation which is called small O notation. How can we prove that this is order of x square? It means that we have to show that f of x mod is less than or equal to some constant, and we should prove this as x square mod, etc. So how we start? For example, you say that x is greater than 1. Where this come from, you will understand that how we have assumed that x is greater than 1. Okay, but so what we do, we multiply both sides with x, we get x square is greater than x. We also notice that x square is always greater than 1, since when you put x greater than 1, for example, you put x is equal to 2, you get 4 greater than 1 over here, 4 greater than 1, so on. So x square is always greater than 1, x square is greater than x since x is greater than 1. X can be greater than 2, x can be greater than 3, so on and so forth. Okay? It's up to you how you decide this to prove that it is order of x square. Okay, so x square plus 2x plus 1, when you put the value for x greater than 1, it will always be greater than 0. Then what you do, we replace this x with the bigger value. It means that we write x square plus 2x square. Then we replace this smaller value of 1 with the bigger value. So we get x square plus 2x square plus x square. This will be equal to 4x square. Although there is an inequality, but you can also write this, since this is just a sum, so we can write this as 4x square. So it means that here x square plus 2x plus 1 is less than 4x square. And if you compare the definition of big O notation, so you can see that this is called f of x, this is called c, this is x square, which is g of x, this is g of x. And what is k? The k is this value which we already discussed, x is greater than k. So here we have c is equal to 4, k is equal to 1. For values of c4 and k1, this inequality holds. So that's how we define the growth of a function. You may also probably try x is greater than 2. You get the same answer from that. If x is greater than 2, multiply with 2x square, x square, multiply both sides with 2x, you get 2x. And then we already know that x square is greater than 1. So we have x square plus 2x plus 1, which is less than, replace this 2x with x square. We have x square plus x square plus x square, which is equal to 3x square. Since we replaced this value 1 with upper value, upper bound, and for 2x we replace this with x square, that is x square. So here this is your k, so k will be equal to 2, and here we have, for example, 3, which is c is equal to 3. So that's how we prove that how one function is less than or equal to g of x for some constant c, and Thank you for watching.